Welcome to another eddycurrent.com action video. This will probably be one of the most complete videos ever made on eddy current calibration. We have lots of samples to show you today. So this is kind of an overview of what we're going to be looking at. We're going to look at tubing standards, thickness standards, non-conductive coating standards, array probe standards, rotating probe standards, all sorts of things. So let's get started. Docking the iPhone camera here, so give me a second with the logistics. All right, so to begin, got to take a swig of the old Dunkin' Donut. Let's first talk about calibration. Now, if you've ever been through an eddy current training class, which you probably have if you're watching this video, calibration is the process of using a known standard and then using those known values to calibrate an instrument to measure what you're trying to measure. So you have to have known like flaw types, flaw depths, flaw dimensions, and of course you want to be using a material that matches what you're testing. So if you're going to be testing thin aluminum on an aircraft, you don't want to calibrate using a piece of carbon steel because all your phase settings and amplitudes will be way off. So that's just to know about calibration. Now there are annual calibrations, which some procedures dictate that you get your testers calibrated annually. Some places do it, some don't. A lot of the military, I used to get some testers in and they would have a sticker right in the instrument, no annual calibration required. Calibrate at each use. So the calibration that's done in the Cal Lab is really inputting a known source, like a known frequency, and making sure that the instrument responds accordingly. For the ASME code for tubing inspections, the linearity of the equipment has to be checked and it has to be within a certain tolerance. So the expected output needs to match the input within some pretty tight degree of tolerance. But then when you hear eddy current techs talk about calibration, they're usually not talking about annual calibration. They're talking about calibrating the tester when they going out in the field to start a job. So that's setting probe motion horizontal, maybe adjusting your gain settings, vectoring your flaws in a specific rotation, creating mixes, creating depth sizing curves, things of that nature. So that's the more common term that we're talking about when it comes to eddy current calibration. Now, what are some known samples? Well, this block right here, that's a calibration block, not for eddy current, but I believe, and I'm not a mag particle expert, but that looks like a piece of carbon steel of a very specific weight that is used to test the strength of a mag particle yoke. See if you can pick it up. If you can't, you got problems maybe. And then had an RT guy in here. He got a bunch of these calibrated metal shims of all different types of metal and varying degrees of thickness. Obviously, he was using that to calibrate something. Then, for eddy current testing, we have, you always hear him talk about measuring paint thickness or other types of non-conductive coating. Here you have calibrated shims. And on the little pack, it gives you the measurement or the thickness of each one of these different color shims. The only problem I have with this sometimes is they say tan is 4 mils. Well, which one is tan? I guess it's this one right here. If you're colorblind, you might need a little help with this one. That's brown, gray, matte black, coral, not pink, coral, orange, etc. Maybe it's salmon or salmon if you're from Wisconsin. Okay, then what else do we got going on here? The standard EDM notch block. Nortec sells a kit of these. I believe there's 5 different materials in there, such as titanium, 304 stainless, some type of carbon steel, common aluminum aircraft, and magnesium, I think. Zinc. I'm not sure, one of those. I do know that one of the blocks, I think it's magnesium, it's always corroded because obviously doesn't respond well to the environment. So this block has 8 mil deep surface breaking notch, 20 mil deep, 40 mil deep. So you use this to calibrate your tester when you're looking for surface breaking cracks. This is a bolt hole standard for doing for doing open bore holes, such as fastener holes when the fastener is removed. Obviously, you wouldn't use this to calibrate a tester if you're scanning airplane wings for surface breaking cracks. So you have a specific type standard per the application. Then here we got this is from the Eddy Current Museum down here. And we've just got a bunch of different types of tubing, and this is probably to show some engineers that, hey, we got a lot of stuff going on in the plant. We got Monel, we got titanium, 439 stainless, Inconel, aluminum brass. All of these different materials would require different calibration blocks or tubes. Because if you don't, your test is basically a no test, and we don't like that with Eddy Current. We want to have a good test. Next, what do we have? When you get into aircraft, calibration standards are only limited by your imagination, kind of like coil designs. So if you need to inspect something, but you don't have a calibration standard that you don't think will help you, call up a place like Flaw Tech or PH Tool or Ecutech. They'll be happy to design and make a cal standard to fit your needs. Now this, I think, is... I'm not an aircraft guy. I don't have an AMP license, but I think this is from a piston or something. I know it's part of some landing gear, but it's got some threads in it, and those threads have some cracks. So I've got, see that little crack at the bottom there? And then there's one on the inside towards the top of those threads. Here you have a threaded eddy current coil that it's the same diameter as that hole. And it just screws right in there, and as you pass over those flaws, you get a nice big whopper of a signal. Then on this other end, there's a smooth probe that goes in there, and there's also some cracks in that inner diameter. And it's kind of flush, so it fits it perfectly, and you just go in there and you rotate the probe around. It's got some differential driver pickups in there. And let's see what else we got in here. If you're doing aircraft and you're only doing a specific material with specific hole sizes, you might only need a couple of standards that have your right hole size. So, and then of course, the aircraft manufacturer or maybe your employer, they might have a procedure that says, hey, it's critical that we find flaws of this minimum size. So depending on that, it may affect the size of the flaws that you put in these cal blocks. Now with aircraft, you'd think that cracks of any size would be important, and they are. I remember seeing a procedure one time, it might have been out of the Air Force. They said if your plane is carrying bombs or people, you need to treat every inspection like there is a crack, and you got to keep looking until you find it. Only problem with that is if there are no cracks, you'll be spending a lot of time looking for them. Okay, we got some more cal standards here. Just a variety of different materials, different hole sizes. And some of these aircraft fastener hole cal blocks will have the EDM notches in there as well. So this is a pretty simple combo standard with EDM notches and holes. If you have one of those, then you don't have to have a separate block and a separate fastener hole standard. This is another aircraft standard that's got a couple fastener holes, and then it's got some pretty small surface breaking notches. Then it's got some deeper ones over here. But see, this one also has a radius in it. So when you're doing wheel bead seats, you got that little curved area in there. And there's some cracks in there. Like there's one right by my thumb there. I don't know if you can see it or not. Anyway, trust me, it's right there. And to get in there, obviously you have to use a small coil, preferably with a contoured shoe on it. And usually, you know, the aircraft, they're going to have specific probe part numbers called out for doing specific exams because they want to have the best fit for the application. Okay, next, moving on. Now, when you really want to get precise with the bolt holes, fastener holes, and you're looking for critical sizes, then you can get this nice set. I got this from a place out of Texas. This is from Boeing Surplus. Each one of these little cow blocks here, if you had to pay for it, I mean, it'd be probably $400 or $500. Anyway, this has hole sizes from pretty darn small all the way up to, what's that, 1.5 inches? And these have, I would say 5 or 6 different cracks in there. Then, of course, you got a big circ in the middle, right? When you got the two blocks attached together. But there are a variety of axial and circ flaws at different depths and on the edges with these. So this is what you'd use when you're calibrating to find some real small cracks in some fastener holes. Now, you're looking at some Nortec instruments here. You can calibrate these testers to do conductivity and thickness testing. Now, as you know, all modern testers usually have a chip built into the probe or the scanner. So when they're hooked up to the instrument and you turn the instrument on, it'll recognize what's attached, and it will recommend settings to help you set up your test instrument quicker. Well, to do the conductivity and liftoff tests in the most automated way, you have to use a specific conductivity standard, like from Olympus, for example. You can still do thickness testing and liftoff measurements, but if you're not using the specific conductivity probe, you'll have to set up those curves manually. And you know, that's what calibration is all about. And that's probably it's another way of separating a true technician from just a button pusher, right? Because if it's not automatic, you know, just think about the McDonald's drive-thru when the cash register breaks. They can't make change because they don't know how to count back change. They never learned, right? But if you learn how to manually calibrate your instrument, you know, using the phase and amplitude controls and the test frequency, which, by the way, is the most common operator selectable in your setup, you know, because you usually can't change the test material. Usually you've got a probe, but you can adjust the frequency up or down to give you the adequate depth of penetration, sensitivity, resolution, and whatnot. These instruments are non-calibrated instruments. Now, that could mean a bunch of things. It could mean that they never got calibrated from a cal lab, or it could mean that the calibration certificate has expired, which in this case, only one of them has, the one in the middle's got a current calibration because I just got it back from the shop. And it could also mean that I'm speaking of calibrated instruments in a more broad term. Now, when you're speaking of it in terms of type of instrument, take a look at this beauty over here, this relic. I got to adjust my logistics here so you can see it. That's a Nortec 8L. All right. Now, I'm not favoring Nortec, but this is part of my collection, and I got to incorporate in the videos when I can. I could have easily used the Hawking locator out of Great Britain for this test because they are both non-calibrated testers. And again, the sense that I'm getting at when I'm talking about this type of calibration is a calibrated display. I guess that's the proper term, calibrated display, is set up to measure specific things. So Nortec made an instrument very similar to this, and right in the display it would say conductivity in IACS. And then right in the front of the instrument they'd have a couple cal blocks, right? Aluminum and copper or whatever, of known values. And you set up the instrument specifically for measuring conductivity, and the display itself says, you know, 20% IACS, 50% IACS. But you'll notice on this screen, it says microamperes DC, amperes, sorry. And you could just well put a piece of tape over that. You don't really care about that label. What you're more interested in is the 0 to 100. And because it doesn't have a calibrated display, it gives you the flexibility to set up a wide variety of tests using this simple tester. So you got a level control, a gain control, then you got your X and your R. So this is manipulating your inductive reactance and resistance of your coil. Those are two coil properties. Now, I could go in here without a procedure and kind of wing it, because I remember using these a while back, 30 years ago, a while back. And if you have a procedure, they're pretty easy to set up. You're just tweaking in the coil properties to be super sensitive to a specific type of material. And once you get it dialed in, you'll be able to minimize liftoff. A lot of these have a train button on them, so you can just lift the probe up and down a few times and it will recognize that as liftoff, as opposed to a change to material conductivity, permeability, etc. So very versatile instrument, but it's got a non-calibrated display. That's not a bad thing. It's a good thing. Unless you just want a tester that's, you don't have to even think. Then maybe you want to get a calibrated display. Now, getting back to the Nortec 600, and then to the right of that you got the 500, and over there you got a 2000D plus EMI. I asked James Bittner one time what the EMI was for, and he told me that, actually not James, I talked to Ronald Bowe. He used to be a Stavely engineer. And he said the EMI, it doesn't do much to the instrument other than it was made to very specific requirements for controlling certain RF parameters, and it was a military option. So if you're shopping for a Nortec 2000D plus, but you're like, oh, I really want the EMI, you're not going to see any additional features with it, but you might have to pay a few $100 more for it, because people don't know what the EMI stands for, but it's not going to change the effectiveness of that tester at all. All right, let's talk about tubing for a few minutes. When you're testing for tubing, first thing you're going to ask is, what type of tube is it? And some of your responses that you get from your client might be, well, it's prime surface tubing. And I'll be honest, I've been doing tube testing for 35 years, and I never knew what prime tubes were. Now you might ask yourself, if you don't know what prime tubes are, how can you be an expert at tubing exams? Well, I work in the power generation business, and the only tubes that I've ever inspected don't have fins, right? And prime tubes, prime surface tubing, are tubes without fins. Since that's the only type of tubing in the plants that I work for, we didn't have to call them anything. Prime versus finned, enhanced tubing. We didn't have to use those terms. They were just, everything was prime. But now you know what that term's for. Also recently had some conversations with a bunch of balance of plant heat exchanger engineers and also eddy current technicians. And they schooled me on the different types of tubing that you would find in chillers and air conditioners. So there, you've got prime surface tubes, but then you've also got enhanced tubes that have either fins on the outside or fins on the inside of the tube. And you know, when you have fins, now you've got another thing that can affect test coil impedance, which can affect the little dance that your impedance point does on your test instrument, and it can really make analysis difficult. When you're doing steam generator tubes, one of the requirements from the ASME code is that you use a multi-frequency tester capable of creating a mix to mix out the signal from support plates, so you can find flaws underneath support plates. So mixing doesn't always work great when you have fins in copper tubes. So, you know, there's a couple things you can try. Eddyfi has an array probe. I think it's called a high definition array probe or something like that. That it's got something special in the design that's supposed to enhance detection of ID pitting in copper fin tubes. I could be wrong, but if you call Eddyfi, they'll be able to fill you in on what they got. So yeah, the HVAC and the chiller industry, you know, they go about things a little bit differently than we do in nuclear. And a large part of that is because the consequences of a missed defect on the nuclear side, carries a bit more consequence or importance, I guess you'd say. If you get a hole in an air conditioning tube in your AC unit, you're going to lose a little bit of efficiency, but there's not like a radiological concern. So if you miss it, well, that's not desirable. But if you miss a defect in something that's nuclear or an aircraft, it's a much more consequential situation if you miss it. So now that's enough about HVAC. Actually, one more thing about HVAC. I also recently learned that a lot of the HVAC and chiller inspections, they're performed a lot of time by one or two guys that show up at site, often one guy, and they analyze data on the fly. So they push the probe in, they got the tester running, and they're just looking at the screen as they pull the probe out. And if they see a flaw, they report it. If they don't, they move on to the next tube. And oftentimes they do that without recording the data. So if you want to go back and look at the test data the next day or week or month, and if you didn't record the data to a thumb drive or hard drive or some other storage medium, you can't go back and look. So if you have a modern tester that's got the ability to store your raw data, you should do that because it can come in handy, and you can also probably charge more for your services if you have that capability. All of the big heat exchanger inspections in any sort of regulated industry, you have to record the data because you need it for trending. And also so you can do look backs. Like if you got a suspected tube leak, hey, go look at the data from last March. You can do it because you have it in some sort of storage medium. Also, sometimes you learn things from your, if you have a tube pulled and you do forensic analysis, and you get a report back from a metallurgist that says these are the diameter flaws in your depths, you might discover that the calibration technique that you use to size those flaws is not as good as it could be. So if you want to go in and reanalyze the data using this new intelligence in a new setup, you got to have access to the raw data. So you'd have to have it recorded. Also, they don't always use mixes in HVAC and chillers. They should, if they got the capability, because it's just another tool in your toolbox. Just like with the modern testers, you're not limited to just a Lysigoo screen. You can have a strip chart, or 2 strip charts, or 6 strip charts, and you can arrange the screen in such a way that you can most effectively evaluate the data using all the tools at your disposal. So just a lot of things to consider there. This happens to be a calibration tube from steam generator tubing, and the ASME code says that you have to have at least 100% hole, 0.52 in diameter for certain tube diameters, and then a 60 and a 420s. When I say 420s, there's one every 90 degrees around the circumference. Now, the reason they do that is when you make a calibration with a bobbin probe, it's desirable if all of your signals are roughly the same amplitude, so your setup is easy. And is easy the right term? Anyway, they want the flaws to all be about the same size. The amplitude of the signal displayed on your Lysigoo screen is a function of the amount of metal, or the volume of metal, that is displaced or missing. So if you take a small drill hole and you took all those little filings out and you put them in a little pile, it's going to be of a certain volume. Now, when you go to the 60% flat bottom hole right here, that's a little bit wider, and it's not 100% through wall. But the volume of metal that's milled away or drilled away is designed to be about the same as the volume of the metal taken away from the 100% hole. That will give you about the same size signal, because signal is based on total length, width, and depth of the defect, or the discontinuity is probably a better term. Then when you go to the 420s, because it's shallower, if you're going to remove the same amount of material, you have to make the diameter of the flat bottom hole wider. And they put 4 of them in there because 20% is pretty shallow, so you got to take 4 of them and a wider diameter to get the same amount of material missing. Now, if you got all different hole sizes, how are you going to tell the difference? Which one's 160 and 20? Well, that's where the phase analysis comes into play. So on these non-calibrated display testers, you can use the test frequency and your instrument settings to separate variables. So if you set noise horizontal, depending on your test frequencies, different flaws will vector a different phase angle. So probe motion, we'll just say has, we'll say we set that to 0 degrees, right? If you have a 5% ID groove or something, your separation angle is only going to be a couple degrees off of liftoff because it happens very close to the probe. But as you get deeper, that phase or that signal on a given frequency, so this is like 400 kilohertz, as it gets deeper, it's going to rotate towards the 100. And then you set the 100% hold to 40 degrees on pretty much every differential channel, at least if you're working to ASNT code. And then as you translate the probe past the 60, you phase your signal is going to be more vertical. And then your 420s, it's going to be over here about 100 degrees, 120. The ASME requirement is that if you set the 100% to 40 degrees, the signal from your 420s has to be at least 50 degrees, but not more than 120 degrees from the 100 hole. So that means your 420s should be between 90 and 160 degrees. So it should be somewhere over in here. Now, when you're coming up with test frequencies, there's a couple ways you can do it. And you know what? I'm really caught off guard now because this is the first time I ever made a video that I didn't have my slide rule handy. But it is next door. I could go grab it. But I don't need to. When you're coming up with test frequencies, you can use 3 or 4 methods. The first one is you can use the Hugo Libby / Franklin depth of penetration calculation, and you can use that. But that's a little cumbersome. I never use it. I mean, I know how to use it, but I don't use that. The way I like is the Canadian technique, F90. I always say the Canadians are some of the best at eddy current, and they are. But their concept is you come up with a test frequency, F90. That's your optimal detection frequency. And I don't throw the term optimal around there unless I follow it with what it's optimal for. So if I say this is your optimum test frequency, optimum for what? Optimum for detection. That's what F90 is. And an F90 frequency, whatever that frequency is, it's going to, when you rotate noise horizontal, it's going to take the phase separation from shallow OD flaws and stick them pretty much straight up. So you have 90 degrees phase separation angle between ID surface and OD surface flaws. Having them in a smaller window like that, depending on how you set your phase, you're going to have a increased likelihood of detecting those signals as you're looking at miles and miles of tubing data every shift. And then once you calculate your F90 frequency, it's simple to get the other 3 frequencies because you're always running 4 frequencies, typically with bobbin. So if F90 is calculated to be 400 kilohertz, you would just double it to get your optimum sizing channel, or often called your prime channel. So if it's 400 for the F90, you use 800 for your prime channel. And then you take F90 divided by 2, so that would be 200 for your third differential channel. And that frequency, F90 divided by 2, is often used as a mix component in a 2-channel mix, which you would use for mixing out tube support plates to find flaws under supports. And then you're going to have a 4th frequency, and that's typically going to be prime divided by 10. So if 800 was our prime, 80 kilohertz would probably be our 4th frequency. And that is typically to help you locate tube support structures and to help you confirm things like deposits and permeability. You know, when you use multi-frequency test instruments, like all these ones you see here, except the one on the right, the green one, that's just a single frequency beast, although you can adjust it. Let's see here. Yeah, so the ASME code says you got to have a multi-frequency tester if you're using steam generator tubing. You got to be able to operate in the differential and absolute mode. It must be capable of performing a 2-channel mix. And there are some other requirements. One of them is don't pull your probe faster than 12 inches a second unless, and that's the big word, unless. 12 inches a second was probably standard about 40 years ago or so, but as test instruments got more robust and they were able to increase the instrument sample rate, or the rate of how often your signal from your probe is sampled and collected and stored and all that good stuff, as that rate capability went up, so did your pull speed. So you can go faster than 12 if your tester supports it with adequate sample rate, frequency response, etc. So we talked about a lot of ASME code requirements when you're doing nuclear tube exams. Now let's bounce back over to aircraft for a little bit. So if anybody's shopped around for aircraft standards, they're not cheap, and you never find them used, right? Because they don't go bad and they're valuable. One of the best tools if you want to increase your confidence as an eddy current practitioner is to, get a tester or two. Now, if you're only a surface guy, get a bob and probe and get a couple tube samples, play around with it if you've got any interest in it. I'm primarily a tubing guy, and tubing inspection is more difficult than surface. Maybe if you're a surface guy, you don't like that, but seeing it on both sides, there's just a lot more components to tube testing. First of all, if you're doing aircraft, you have the option a lot of times to go single frequency or dual frequency. But when you're doing tubing exams in the nuclear environment, you're always using 4 frequencies, and you're constantly flipping between those frequencies to separate variables. You want to use certain frequencies to confirm tube deposits, maybe fouling on the OD of the tube, to check for clogged flow slots in broach support plates, to confirm magnetite, to confirm whether something's ID originating or OD originating. Then you got your 2-channel mixes for suppressing one variable like tube support plate signals that could mask flaws. Then you got your 3-channel mixes, which are often called turbo mixes. That's just kind of a term that somebody used once and it stuck, so that's kind of the industry term. There's just a lot more in the setup. And then when you get into array probe testing, now you're not just talking about one surface probe, on a pencil probe head. You're talking about bands of multiple coils. Now, I'm not a probe designer. I haven't looked at an array probe head in a while, but I think some of them have like 2 bands of maybe 8 coils in each. So that would be 16 coils. And then each one of those coils, might be operating different modes. I'm not sure. Call 85. They'll tell you all about it. But the point is, there's a lot of channels and there's a lot of data. And that's one of the challenges that's facing the nuclear industry today, is that everybody wants to do the array probe because it collects a lot more data than the bobbin probe, and it provides more information about certain types of flaws. For example, if you find a flaw at a geometry and you're not really sure if it's axial oriented or circumferential oriented based on the bobbin probe signal characteristics, you might want to run the array probe. Also, the regulations will possibly let you run the plant a little bit longer if you did 100% array probe testing. So naturally, every plant wants to use the array probe. The array probe collects gobs and gobs of data. And, the NDT industry is similar to a lot of other trade industries, that skilled labor, is kind of disappearing rapidly due to the retirements of the baby boomers. And, now with the digital economy, there's a lot more options for young people that want to make big bucks. There's all the AI jobs, and there's social media jobs, and there's just a whole sorts of things competing for the bright young minds. So anyway, we got to use automated testing to keep up with all the array probe testing and steam generator tubing exams, because there's tons of data. The outage windows are getting shorter and shorter. It used to be that refueling outages were 6 weeks, 2 months. If they were doing some kind of hefty repairs, they could be in a 6-month outage. You had all the time in the world to do eddy current testing. Now, the eddy current windows are down to like 3 days, and you're doing 200 miles of tubing in 3 days with multiple probe types, different test exam extents. And you got to leave time for diagnostics and all that other good stuff. So automated data analysis screening tools are pretty much the norm these days. And they work a lot better than they used to just because they're more advanced. All right, so we were getting back to aircraft standards. Oh, yeah, the hard to come by. I had the good fortune one day, I was on eBay looking for something, and I came across a listing for, I think it was this particular cal block here. And because I've been looking for aircraft standards for a while, I immediately recognized this as a valuable Eddy Current Calibration Standard made out of aluminum with flush mounted rivets with some cracks coming away from the fasteners. Now these are installed rivets, obviously. This is something you use a slide probe with. Now if you look at the side of a big jumbo passenger jet, you can imagine how many rivets are in an airplane. Now, if any of you aircraft guys are watching this, maybe you can chime in the comments and give me an estimate for how many rivets are in a full-size jet. It's kind of like how many grocery store items do they have in Publix? Any guesses? 5,000, 10,000? It's more like 50,000. And I would guess there's probably at least 50,000 rivets in a big jumbo jet. So there's just a little useless trivia for you, but trivia is interesting. All right, so I was gonna buy this. I was interested in it, but I was a little hungry, so I got up and I made a sandwich. And when I came back, I looked on eBay and there was like 15 people watching it. So I'm like, oh boy, I better buy this quick, otherwise I'm going to lose it. So I bought it. And I saved the lady as a seller. And then a couple days later, I think we had this one on there. And I didn't waste any time with that. I snapped it up in an instant. This one's got layers. See, this has got 2 layers, thick on the back, thinner on the top, and even the top one's, probably 1/4 inch. That's getting pretty deep for eddy current testing. So you could use a couple of types of probes on this. You could use a sliding probe to do these flush mounted rivets, and you can inspect these lickety split. I mean, it's actually kind of satisfying to use a sliding probe because you're scanning over the material pretty darn fast. You keep getting that repeating pattern, these high repetition signals. Now, if you don't know what high repetition signals are, they're signals that repeat a lot. And usually the signals that repeat a lot are things that are supposed to be there, like rivets. Your test instrument, usually it's desired that you have a storage display for non-repetitive signals. Now, what does that mean? Well, if you go into the display settings and the screen settings, you can adjust the persist time of the impedance trace on your screen, kind of like the Etch-a-Sketch, right? You got to shake it to erase it. Well, here you just hit the erase button. But if you set the persist up for at least a couple seconds, every 2 seconds it'll erase what it saw 2 seconds ago. But what that will do is if you happen to blink or sneeze or get distracted or look away for a minute, if a non-repetitive signal like a cracked rivet hole would show up, you looked away for a second, you look back, it'll still be stored on your screen. So that's why we have storage capability in our screen. So it gives us a chance to actually visually detect those non-repetitive signals. Okay, so I bought that standard. Then I emailed the lady and I'm like, hey, if you got more of these, just drop me a line because I'll take them all, right? Well, so then I got this one. This one's got 1, 2, 3, 4 layers, 4 different layers with different hole sizes, and there's cracks in every hole. This baby here is probably $5,000 for this one. Now, one thing I jumped over this, you'd be using sliding probes for the flush mounted rivets. And then, this is some pretty thick stuff on the back. Can't use a sliding probe because it'll hit these rivets. So you would use ring probes or donut probes. If you want to go and check these, obviously you can only use a donut hole up to a certain size because it won't fit over the hole. But a lot of times, the ring probes, you can get small ones, but there's also very big ones, heavy, with a lot of wire in them because they can get a little bit deeper. So then, now those are all manufactured calibration standards, right? They're made in a machine shop. But then you got some of these, like this panel from a F28. This is only 2 layers. 2 layers. So they cut a piece of this out and then they machined some. They got a crack there on the right. And then I think if you flip it over, there's another crack. So on the opposite side, but on the back, spanning about 2.5 rivets. So this is what you call natural. Well, I take that back. This is a natural sample, but it's machined flaws. So it's kind of like a hybrid. Then I got another one. Now what I did with this one, some of these were marked. So these came from a training department from an airline company that went kaput. So obviously that's why these became available. But this one has some flaws in these rivets. But what I wanted to do was, when I was checking out my sliding probe, trying to make sure that it worked correctly, I wanted to make sure that I could find a crack in this particular material, not just in my aluminum cow block that might have been a slightly different material. So what I did was I took a couple pieces of Reynolds wrap, cut them off here, and then I butted them together so there's basically a simulated very shallow crack here, and then I put some non-conductive film over it. So I would just scan over this and make sure that I could see the flaw, and then I would go scan the rivets. So that was just to sort of help me understand my calibration a little bit for that panel. Now I've got 2 more there. But then if you look over at this box, I got panels and I got some T-joints. Then I got more 3 layers with different rivet sizes and types. Then here you've got, this has got some weird kind of scallop design in it. And then we've got big spot of like corrosion on the second layer. This is for bond testing, if you've ever heard of a bond master instrument. Then here we got some different types of protruding head rivets and flush mounted rivets. And James Bittner knows what that one is because he used to inspect, I guess, this DC9 component. So this is a cow flaw from an actual part that's got some machined notches in it. And there's also a special probe bottle that went along with this specific exam. So like I said, a lot of times the test procedures will dictate what equipment you use. Now, a lot of you are probably saying, wow, that's a pretty nice collection of calibration standards. And it is. I forgot to show you this one. This is a plate used to calibrate surface array probes. And this has a big wide groove going across it. I believe that's to set voltage. And then there's just a series of flat bottom holes. This one doesn't have any cracks in it, I don't think. But you know, you just flip it over and you put your array probe on it and scan over the surface and be able to detect the flaws if you're using the right frequency and you've got the right coil parameters. I'm going to make another video, maybe today, depends on how ambitious I get. But I want to talk about coil size a little bit, big coils versus small coils, and some considerations you need to make. But getting back to my cal standards, and you know, not everybody's going to have a nice set of calibration standards like this. Calibration standards are the tools that you're going to use to build your confidence that you're able to detect the flaws that you're expected to detect. And if you don't have the right calibration standard, the right material with the right type of flaws, and you're using the right tester with the right probe, with the right settings, and the right test frequencies, you can miss flaws. The only way to know that you're going to detect them is to have a representative cal sample. Now, if you're just trying to improve your data evaluation skills and, become more competent as a data evaluator, there are a lot of ways you can make calibration standards on a budget. Now, you can't make a budget calibration standard with a Reynolds wrap and then go use it on the Boeing. You're not going to do that. It's not allowed. You've got to use very controlled, pedigreed samples. But to test your knowledge and to understand eddy current theory a little bit better for things like lift-off and thinning and permeability changes and deposits and support structures, you can easily find materials on Amazon that even on the most modest of budgets, you can make your own cal standards. So what is this one? I have to think back of when I was making this, and I was probably wanting to demonstrate F90 frequencies and also the effects of placing one standard depth of penetration at the back surface of your part versus a higher or lower frequency. So what I needed to do was create I had base material, and then all these little things here, this is all aluminum. These are aluminum name tags that you can engrave your name in or whatever, right? So I just bought a stack of those for $5 or whatever they were. And to make the first surface breaking crack, and it's not through wall because the crack is simulated from these two plates being next to each other, but they're on good base material, right? So if I look at that, that's like a millimeter deep surface breaking crack on this aluminum sample. And then I just put some tape over the top so I wouldn't catch my probe on the on the crack there. Then to make it a little bit deeper, because I wanted to see how the phase lag would increase or the separation angle between liftoff and a deeper surface breaking crack would behave. So I just put two plates here, and butted them next to each other. I glued it all down with super glue, put a little piece of tape over the top so it wouldn't catch. And then I just continue on. I did 3, so that's going to be a really deep one. And your phase lag as you get deeper is only going to increase to a certain phase, and then it's going to stop increasing. And that has to do with the weighted average of eddy current, the way it impacts your test instrument, right? So they're only going to get to a certain phase if they're surface breaking. Now, if they're subsurface, then you can get a lot more phase lag. But if it's a surface breaking crack, the deeper you go, it's only going to get to a certain phase, and then it's going to stop rotating clockwise. And then the last two, what do I got going on there? The last two, 1, 2. I'm not sure what I did with those last two there. I'd have to dismantle this cal block, or I would just have to turn on one of my instruments and do a little investigative eddy current testing to determine what these last two are. Okay, so that one, I bought a foot long, maybe a 12 by 6 piece of aluminum for like $15. And then these tags are like $5. All right, and then, if you read that Fundamentals of Eddy Current Testing book by Donald Hagemeyer, one of the pioneers of all aircraft eddy current testing, you're going to see a lot of impedance graphs and XY displays and vector diagrams. And towards the back of that Fundamentals of Eddy Current book, you've got some thickness loci, thickness curves. Of course, there's liftoff curves, conductivity curves, but one of the curves that's very, very important to understand in eddy current testing are the thickness locus. So with this particular standard that I made, homemade, got some Reynolds wrap. Reynolds wrap is your friend for cheap eddy current standards. And I just started off by making one layer, which is probably like, a 1,000th of an inch, maybe a little bit thicker. Then I would put 2 layers, 3, 4, 5, and so on, up to like, maybe 12 or 13 layers. And by touching my probe to each one of those, if you vector ferrite to go straight up, and you just start to touch each one of those, the first one's going to go to the right a little bit, and then the second thickness is going to go down to the right a little bit more, and then it's going to keep on doing that until it comes all the way around and touches the backside of the conductivity curve. Now, I asked my old mentor one time, why is the conductivity curve on the inside of that locust? And he looked at me like I had two heads. And he's like, what do you mean? And I don't know if he ever gave me the right answer, but I figured it out later. It's not that the spiral thickness locust comes around and meets the backside of the curve. The conductivity curve is something that you just draw in. You draw it on your screen with a grease pencil or whatever, like a Z-Tecmas 21C, it'll even draw the curve in there for you. But that's just a curve for your visualization, representing different conductivity values. But thickness changes always move in a spiral fashion. And they just curl around, and when they get really weak and you can't get any more penetration, they just stop. And that's the point of infinite thickness. So further decreases in your test frequency won't get you any more eddy current penetration. If you want to go deeper, lowering your test frequency on a small coil isn't going to do anything. It might do something, but it's not going to do much. What you'd want to do to go deeper is get a wider coil. If you've ever looked at Eddy-Fi's lift pulsed eddy current system, they're not using pencil probes. They're using wider coils. Because the pulsed eddy current, in combination with the wider coils, allows you to penetrate, through insulation and through different types of coverings. So you can punch through 4 inches of insulation, and find general corrosion, or it's got to have some size to it. But you're not looking for micro cracks with pulsed eddy current through layers of insulation. It's every eddy current test has its applications that it's good for, right? If you want to find micro cracks, use a pencil probe. There happened to be a really good horse documentary. It's called Buck, and I think the guy's name is Buck Branahan, if I remember that correctly. But he's like the real life horse whisperer. And he was saying that the soul of a horse and the skin of a horse are very, very sensitive, right? And he says their skin is so sensitive they can detect a fly landing on their butt in a windstorm. And you got to think about eddy current testing with pencil probes. You want to find something really small like that, you need something really sensitive, which is a small coil driven at high test frequencies. To use another zoology reference, if you're using a great big wide coil, like one of those lift coils, 3 inches across or whatever it is, and you're trying to find a micro crack, it's like an elephant stepping on an ant. It's not going to feel it. Those large coils aren't going to see those micro cracks. Now the ant will feel it, maybe, not for long. But if you want to detect the very tiny cracks, you got to use tiny coils, high test frequencies. Okay, let me look around and see what else we got. Let me just talk about this cal standard a little bit more. I covered the 160/20 holes, but this has a tube support plate ring in it. And the reason it has a tube support plate ring in it, so you can recognize what a tube support looks like on your strip chart, but you also need an actual tube support plate signal to perform your mix. So your software, it's easy, it's advanced. You just put the signal on your screen, select a couple frequencies, hit a button, poof, the display basically suppresses the support signal, and all you're left with is flaws, hopefully. So when you do the mix, you always have to go back and look at your cal standard to make sure you didn't inadvertently mix out some flaws, because that's possible too. And it's kind of like if you're using a Nortec 500 or 2000, whatever, and you can manually adjust your high pass filter. All these test instruments have low pass filters, band pass, high pass. High pass filters are speed dependent. Like on the Nortec 600, right there, it automatically will adjust your high pass filter as you increase the RPM of your rotating scanner if you're doing rotating fastener hole exams. But it'll adjust it up and down accordingly. But if you are using something that doesn't have that automatic high pass filter adjustment, if you crank your RPMs up, it can attenuate the signal of your flaws, so they get much smaller. you can actually totally wash them out if you use too high of a high-pass filter. So always be mindful that speed is an important factor when using high-pass filters. What do we got here? That's a bolt hole probe from yesterday, a tiny one. And then we got a couple more here. Here's a Cal standard. This is the old swinging magnet. Here we're talking about, was it Leon Foucault? Was Leon Foucault, did he have the swinging magnet, or was it Arago? Arago had the lodestones. I think it was Foucault that had the swinging pendulum. Yeah, it was, because he had the pendulum in the Pantheon in Paris as well. That was for the Lissajous patterns, the earth moving below the pendulum. But this swinging magnet, it's a sort of calibration standard, just a thick piece of copper. And here I just have, these are non-calibrated, these are non-official. But I used a meter and then I punched in 46 IACs on that aluminum, brass, and then copper. And the reason for these 3 cal samples, we'll call them, is to show how when eddy currents are generated in the part, you create the secondary opposing magnetic field per Lenz's law, and it'll slow down the magnet. So first we're going to take the weakest one. I think the weakest one is aluminum. No, brass. So this is just a magnet with it's got 2 really strong neodymium magnets. If you look at the colors, they're lined up so the magnetic flux is all flowing in one direction. So when the magnet's swinging, look at those arrows. That's the way your incoming magnetic field is, coming in hot. And if I just take this back to 90 and let it swing, if I had all the time in the world, I would just let it swing to a stop, but it's going to go about 100 times back and forth. That's not a guess. At one time I had them taped how many times it was, and it was about 100 for a freewheeling swinging magnet. So then we're going to take brass, and there's a little hole right at the bottom, right below where the magnet's swinging. Now, when there was no conductive material below the magnet, there was nothing to slow it down other than the friction from air and probably the friction from this bar. But there was no eddy currents to slow it down, is the point I'm making. So what happens, first of all, before we even swing that magnet, a lot of people think that you have to have alternating current to generate eddy currents in a test material. Not true. All you have to have is a moving magnetic field. The reason we use alternating current because that's the easiest way for us to accomplish the movement of the magnetic field. But if you ever seen an experiment where somebody takes a magnet and they stick it on an aluminum plate, preferably a bar magnet, and you let it go, it's going to slide real slowly down the plate. That's because it's generating eddy currents. And you're not using alternating current. You're using the direct, a one polarity magnetic field, but it's moving. That's where the magic happens. So when I swing this magnet, it's going to generate eddy currents in that little piece of brass. So you probably can't tell, it's still moving pretty fast, but it actually takes from 100 swings down to like 25. See how that damped it quite a bit? Damping is another word for slowing down. Like if somebody was making a lot of racket and spewing off at the mouth, if you covered their mouth up with a cloth, you'd be damping their voice. Now we're going to take aluminum, 46 IACs. What would you guess that's going to do? Well, it's more conductive. It's going to produce more eddy currents. Those eddy currents are going to generate a stronger magnetic field that opposes the incoming, coming in hot magnetic field of this swinging magnet. And whereas the brass was like 25 swings, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, something like that. And then naturally, when you go to the copper, I think this one's down to like 5 swings. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so they have it done quite a bit. Now, I need a little gripper to get that out of there, or just do that. Now, when I made my first eddy current course for Chuck Hellier, NDT legend, when I was in the studio filming this particular video, I had the cameraman bring in a boiled egg, and I put the boiled egg in one of these holes right here for dramatic effect, because everybody likes excitement in these videos, which you normally get with my videos to some extent. But I figured if it slowed it down a lot just with a little copper slug, what would happen if I used a robust piece of copper with lots of mass? So I put that under there. Now you can see that magnet moving. It's not because it's touching this plate, because it's not. There's clearance in there. You don't believe me? You gotta look in there. I don't know if I can see it in there, but there's clearance. The reason it moves is because when that magnetic field moves, there's a lot of mass in that little plate there to generate eddy currents. And what's cool about this is if you hold down the plate with your hand and you move the magnet, you can feel that there's, substantial friction in there. Now in your studies, I remember teaching an eddy current class, and there's the power formula. They talk about watts, and how many watts are expended when you're heating up material. Well, when you're running a test coil through a tube, especially if it's magnetic, you are in there manipulating the magnetic domains, and you're causing them to move. That can generate Barkhausen noise, which is another one of the 70 or 80 NDT techniques that are out there. You can actually listen for those little magnetic domains shifting and turning as they're being worked and manipulated. But all that generates heat, and it's measurable heat, and that extends watts. So the energy that is lost in a material is not completely lost. If you think about that law of thermodynamics, that energy never disappears, it just changes form. Well, your magnetic energy gets transformed into heat decay, right? So there's eddy current heat loss. That's what they're talking about. So if I did this a bunch, and if you had a sensitive instrument, it's probably heating that up a little bit, but not too hot to the touch. But if I had more mass to the copper and a much, much stronger magnet, and I increased the rate of my oscillation, you darn right it's going to heat that up a lot. Probably fry an egg on it. All right, so that's why I use those calibration standards. And then, if you're just playing around in your own lab and you want to have a conductivity set, there's a lot of stores on eBay that sell just little, it's got like copper, aluminum, brass, stainless, carbon steel, probably less than $10. And these work just fine for your education. Now, I once sold a tester, and I was given a pretty cheap price, and the guy goes, "Hey, will you throw in a cable?" I'm like, "Well, that's it's $300." Then he's like, "How about a battery? How about a strap? How about a case?" They almost want you to pay them to take your testers from you. But he wanted a cal block, and I said, "Well, what are you testing?" He said, "Carbon steel." I said, "Surface breaking cracks?" He goes, "Yep." I said, "I'm not going to give you a standard, but I'll make you one," right? So I took some carbon steel. I took a couple of, I had some thinner carbon steel plate, cut it, put it next to each other. That crack is 60 thousandths deep. So it's pretty deep when you compare it to the EDM notches in those other blocks. But your depth of penetration with carbon steel is basically limited to the surface anyway, so that crack could be a mile deep versus a millimeter deep, and it wouldn't make much difference. But all I wanted to do was give him something so he could place his probe on there, determine what the, where the probe motion was, set that horizontal, set the amplitude such that the signal would be, maybe 50% screen height. And I said, this will get you close enough. You'll know this your test instrument, your coil, and your settings are working fairly close. But then when you go to your carbon steel, just go tap on the surface and see where your liftoff comes in at, and you may have to adjust it. So this was just something I threw together so he would have something to calibrate with. Now, what about natural calibration standards? I saw this in my little archive of materials. This had some sort of corrosion on it. This looks like a little lid or cover for something that was on a hinge. But this was actually corroded away. So I'm like, well, that'd be cool to find with eddy current. It's kind of heavy, so it's some sort of steel. So what I did was I just took a little thin piece of, I'm not sure what type of material this is, and I just cut it to shape and I glued it on there. This is actually the one thing I have never tested after I made this little cow block. So that'll be another video. Then, of course, with eddy current testing, we're dealing with thin materials, right? So you can do a lot of stuff with thin materials and layers. So this is a roll of brass that's like a couple mils thick, maybe like 5 mils thick. You unroll it, it's 10 feet long. You can make a lot of samples with this roll. How about this aluminum tape that the HVAC guys use when they're putting in all their ductwork? This works great for making aluminum crack samples. You just cut down some sections, make sure they're square, hold your scissors straight, put them close to each other, and just layer them as deep as you want to go for surface breaking cracks. There's also, we like tested copper, right? You can get your copper tape. I think I got both of these rolls for like $10, and I've been using them a lot, and I've still got probably 50 years worth of thin aluminum and thin copper there. Then I got some other thin name tags for making crack samples. This was a good one. When I was doing some videos on conductive plating over conductive base material. So this is actually carbon steel base material, and I put aluminum sheets of varying thickness on top of the carbon steel. Increasing conductive coating layers always rotate counterclockwise as they're increasing. And it doesn't matter what material you're going to. The thicker the plating gets, the more it will move in a clockwise direction. If it gets thicker, if you're on a lower conductivity material and you're measuring higher conductivity plating, it's going to rotate clockwise on the outside of the conductivity curve. And then it's going to finally meet the curve when your coating thickness is infinitely thick. If you're on a conductive base material like aluminum, and then you are testing like lead plating. I don't know if you'd plate that aluminum with lead, but if you did, it would also rotate clockwise as the conductive coating thickness increased, but it would just be rotating clockwise to the left of the conductivity curve. So those are things you don't really get unless you do these sort of mock-ups. And then, I was scanning this plate. Here I did some copper plating on carbon steel also. But then I'm like, I wonder what these different colors are on here. So I scanned my probe past it, and I was getting radically different vectors on my Lysigee screen. And I'm like, these paints have conductive properties to them. So I'm not sure what this paint they're made out of, but it's supposed to probably be strong paint. It's got some metal in it because this actually went way up in the permeability realm of the impedance plane. So you got to know what's in your paint. You always got to test it and make sure you know what you're looking at. Don't assume anything with eddy current testing, right? So I hope with this video and all this talk about calibration standards and calibration and test instruments, there are a lot of ways that you can, for not a lot of money, go out there and put together a wide variety of samples where you can increase your eddy current skills and your eddy current game. It'll give you much more confidence in the long run. All right, thanks for watching.